Okay, so now we could officially go over the quiz. So let me go back to the quiz and remind you that if we want to find out the chain rule for spherical coordinates with respect to phi, we need that x is rho cosine theta sine phi, y is rho sine theta sine phi, and z is rho cosine phi. So then we can jump to chain rule. Okay, so the chain rule, again, we have f of x, y, z. We got to make this happen. So let's work this out. So we can say that del f over del phi is equal to, well, it's going to be, let's do some copy and pasting so I don't have to keep typing dels. It's going to be del f over del x times del x over del phi. And then plus, and basically you're going to have the same thing except the x's become y's. And then the same thing, and the x's are going to come z's. So copy and paste, change the x's to y's. And then change the x's to z's. Any questions? Any questions about kind of the formal chain rule? Okay, so now we just plug in. The del x, f is a general function, so we can't do anything with that. But del x, del phi, that we can actually compute. And same thing with del y, del phi, and del z, del phi. Those can be computed without too much of a problem. So I'm going to copy and paste this. And let's pop those in. So it equals, again, del x, del phi. Well, x is equal to rho cosine theta sine phi. Derivative of sine phi is cosine phi. So I just get rho cosine of theta cosine of phi. And then for del y, del phi, again, y was rho sine theta sine phi. So it'll be exactly the same, except there'll be a sine of theta instead of a cosine theta. So I can actually just copy and paste it, take the cosine, turn it into a sine. And then similarly, z is rho times the cosine of phi. So the derivative of that will be a negative rho sine of phi, because the derivative of the cosine is negative sine. Equal sign. Any questions at all? Any questions at all on part A? Guess I should write A. Any questions? Okay, let's do part B. Part B says, use the answer from part A to find del f del phi for the function 2x minus 3yz. So now what we do is for part B, I am just going to copy and paste this guy and then put in what we need to. So we're going to use the formula. So I'll just rewrite the formula. And remember, we had 2x minus 3yz. So del f del x is what?
2.
2. Del F del Y is? Yeah, negative 3z. So minus 3z. And del F del Z is? Negative 3y. So that minus becomes a plus, and we get 3y. Okay, so once you have the formula, there's not much to do. You just take the derivatives. Any questions at all on this? Okay, I didn't ask you to do this, but if you wanted to get rid of the y and the z, you can always just plug in y is rho sine theta, sine phi, and pop that right here where it says y. You can't see the y anymore, but where that y is. And then z is rho cosine phi, and you can pop that in for z, but I didn't ask you to do that. But sometimes, like in physics, you want to get it in terms of rho, theta, and phi. Any questions at all on question 1? Okay, let's look at question 2. So let f be a differentiable function, and x of u v w, y u v w, and then u s of t, v s of t, and w s of t be differential functions. Find the chain rule formula for del f del s. So this is just using the chain rule, and what I'm going to do is I'm going to use the chain rule for del f del x. I'm going to ignore the some of the letters because it's easier that way, and then we'll fill it in. So we're going to have del f del x, and will it let me copy? No, it doesn't. So let's go del f del x. So del f over del and again what I wanted, we want del f del s. So by chain rule, that is equal to del oops, try again, del f over del x times del x over del s and then plus, same thing with the y, so del f del y times del y del s. Oops. Uh-oh. Get rid of that. Put it here. Times del f del z times del z del s. And let's pop that in so we can look at it. Okay, but x is a function of u, v, and w. So we need to use the chain rule on to do del x del s with u, v, and w. So then what I'm going to do is I'm going to substitute del x del s with del x del with del x del u del s, et cetera, et cetera. So let's go do that. So we have u, x is a function of u, v, w. That's the important thing. And it's going to get a little long. So we have del x del s becomes del x del u times del u del s plus, and then we do the same thing with y and z. Definitely a challenge to type it, but I can do it. So let's see, sorry, v and w. So del x del v times del v del s. And then plus del x del w times del w del x. And then what I could do is I could basically do the same thing with the y and the z. I'm just going to copy and paste it. And where I see an x, I'm going to put a y. And similarly over here, where I see an x, I'm going to put a z. And I know it's small because there's a lot of writing here, but there's your chain rule. Any questions on that? Any questions on this chain rule? I think there was just one question, no A and B or anything like that. Okay. And again, sorry about the small font, but I don't think I can choose. I don't think I can change that. Let's see. Oh, is there no Z on this one? Let me look. Oh, there is no Z. Thanks. Sorry about that. I was thinking about the last question. So I'll just get rid of the Z. Good. That makes it a lot shorter. It'll fit prettier. So the nice thing that's easy, I just delete it. Much better. And there's our chain rule. Okay. It's messy, but it's doable. You know, if you really needed to find a derivative and you had, you know, some change of coordinates, whatever, then you could do that. And typically in the real world, you have plenty of time. There's no 20-minute limit. There's usually you got a week to do it or something like that, or your client. Any questions at all on this quiz? Any questions? Okay, this is one of those very symbolic quizzes. Okay, it's not like we're looking at graphs and curves and stuff. We're just using the definition of the chain rule. Okay, there was a little bit of derivative taking, I guess, on Pet B, but not too hard. Okay, what I want to do now is I want to talk about an issue, and it's something that we've talked about, and we're going to find out what we've talked about isn't enough. So what we talked about last time, and the time before, actually more the time before than last time, is we talked about how to find a partial derivative with respect to each of the variables. Okay, so remember the partial derivative with respect to x means that if you're going like in the east direction, how steep is it? And the partial derivative with respect to y is if you're going in the northern direction, how steep is it? Right? Do you remember doing that? So we could talk about it. And I brought this map up. And the reason I brought this one up is I'm not sure if it's wishful thinking or not, but this is what I'm hoping that I'm doing this weekend. I don't know if you've been to Susie and Heather Lake, but they're some of my favorite places in Tahoe. Very pretty. I don't know if I'm allowed to go there. That's the only question. If anyone knows, let me know. But I'm gonna, if I can even bike to the trailhead and then walk, then I'm going for it. So here's the question. If you were trying to understand the trailhead, and let's go to the trailhead I'm going to go from, which is from Glen Alpine. So right around here, and then I'm gonna go up this trail, and then a little of the PCH, and then get to Susie Lake. So my question for you is it enough to understand del F, del X, and del F, del Y, where F is the altitude elevation function? What do you think? So do you think it's enough to just talk about del F, del X, and del F, del Y, and then you really understand how hard this trail is going to be to hike? We're going to walk along this trail. Okay. All right. I'm hearing no. The hiker should understand that it's a no. Okay. So let me just give you an example. Let's say I'm over here by this little pond. Okay. By the way, you do this in June, you get bit by mosquitoes really bad in this area. But if you were to do it, what you really want to know is that if you walk along the trail, how steep is it? Does that make sense? And it's not north, it's not east, it's somewhere in between. Okay. And in fact, it's somewhat northwest. Does that make sense? So we want to look at this and we say, well, how steep is it? So that's one thing you might be interested in when you're looking at a trail, is to say, well, how steep is a trail? And you can't just say, well, I know how steep it is north and I know how steep it is east. And that's all I care about. But no, most trails don't go north or east. They do something else, like northwest or something. Does that make sense? So one of the main things we're going to talk about today is we're going to say, well, how do you find the slope of the trail in the direction that you are interested in going? Okay, not just north or east, but wherever you want to go. Okay, so that's one thing you might care about. All right, now let's go for another one. Okay, and this happens to do with something else I like to do. And my guess is most of you probably never done this, but I encourage it if you ever want to do some volunteering out in the forest. And that is I build trails. One of the things when we build trails is you have to say, well, if there are some rocks over here, and because of erosion, the rocks are going to come down, where are they going to go? Are they going to land on the trail? Are they going to land off the trail? Where are they going to go? And in road work, you really care about that because it could kill someone. Okay. Trail work, usually that doesn't happen. But road work, that's a big deal. Well, hopefully you know, or maybe you do, maybe you don't. If we have this contour diagram, and let's say there's a rock right here. I think you can see my mouse, right? Pretty sure you get to see my mouse. Good. So there's a rock where I'm pointing. And all of a sudden, there's an avalanche. Where is that rock going to go? What direction is that rock going to go? North, south, east, west, somewhere in between. Where do you think? Any ideas? Okay, it's going to go kind of southeast. Again, not perfectly southeast, but kind of southeast. So the idea is visually, some of you kind of have an idea of how this works. Okay, but what we want to do is we want to do more than just kind of visually kind of figure out where the rock might go. One thing you might want to do as an engineer is you're going to take this contour diagram, you're going to put it into a computer. And then what you can do is you can computer model where the entire erosion is going to happen for everything here. Okay, you're also going to put where the rocks are all the way through this diagram. And you don't want to do one or another, you're going to program it and let the computer tell you what's it going to look like in, say, 10 years. And then if you know what it's going to look like in 10 years, you say, well, I don't want that to look like that. So I'm going to put some barriers or whatever, I'm going to do engineering work and make this more stable. Okay. especially, again, I do trail work. We don't do quite as much of that in trail work, but in road work, you definitely do that. You want to talk about how do you make your road safe so for the next 10 years, you're not going to be calling Caltrans out every 6 months to clean up the road. Does that make sense? Where do you need to put the netting, things like that. And you do that, that's an engineering job, but it uses what we're going to be doing today. So I wanted to show you this as kind of a motivation behind everything we're going to be doing in this section. Any questions at all on kind of this idea? Okay. Again, if I were teaching this in Kansas, I don't know what I'd tell them all. Nothing moves. So it's nice to be in Tahoe, where actually I can throw a map of where we live, basically. Okay. And again, if you don't know where this is and you've never been here to Susie Lake, Heather Lake, I strongly recommend you go because it's absolutely beautiful. So it's one of my favorites. Okay. Any questions at all before we get into the mathematics? Okay, so let's do some math. So I'm going to start out with the gradient. And this is a definition. And what we already know how to do is we know how to find f sub x and f sub y, right? And those are partial derivatives. But what if someone said, what is the derivative of a function? Which one do you want to choose? Which is more important? What do you think? Nobody wants to tell me? Okay. Okay, the answer is this is a trick question. It's a tie. You can't say f sub x is more important than f sub y. Right? They're both important. So here's the definition. We kind of cheat, and we're going to define the derivative as both. And you can do that if you remember what we did earlier in this class. Any guesses? We did partials, but I'm saying very early in this class. Not just like early, like last week or something, but I mean really early. So we're talking a month ago.
Parametric equations?
What's that? Parametric equations? Yeah, not the one I was thinking about though. So we'll get there. Again, I don't expect you to just know it, but let me show you. Okay, let's make f of xy be a differential function. Okay, and again, from what was that, Friday, we talked about what it meant to be differentiable. Basically, it means you take derivatives, okay, and they're continuous. Okay, so let's suppose we have a differential function. Then the gradient of f of xy is, and now there's different notations on talking about this. So let me write them out. So one is sometimes you'll see grad of f of xy is one notation. Another notation you'll see, and I didn't check ahead of time, I hope I can get it. It's not here. Really? Maybe it's there. Okay, bad luck. So I'm just going to do this even though it's not quite. So let you know it's not this triangle, but I can't, unfortunately, the program, the Google Docs I'm using doesn't allow it. Take this and turn it upside down. Can y'all imagine that? So it's an upside down del. Okay, so the grad is also written this way with an upside down delta of f of xy is equal to, and again, as I mentioned, we got to think about what we did earlier this quarter. And what we did is vectors. So it's going to be the vector f sub x, f sub x, comma, f sub y. Okay, and again, this triangle, turn it upside down when you write it, else whatever, because that's not how it really is. Any questions on that? So this is the old, well, we know that the partial with respect to x is important, but the partial derivative with respect to y is just as important. So we're going to just say, well, we're going to be stubborn and say, well, I'm just going to want them both. And the only way, or the main way we get two things in one creature is a vector. And it's the vector fx comma fy. Okay. Notice something interesting. Fx is a number when you plug in an x and y, and so is fy. This really is a vector. Okay, it's a two-dimensional vector. Any questions on this? Any questions? Okay, just a note, and this is kind of important, is that grad, or this upside down triangle, is a function. What's the domain and what's the range of the function grad? And this is a type of function you've never seen before, but it's defined, so you should be able to tell me the domain range. Fx domain. Fy range, not quite. It's a good try though. Okay.
Well, the output is a vector.
Good. So the range, I'm going to use the word range though. The range is a vector, okay, in R2. And the domain is the set of all differential functions. So this is a function on functions. Any questions on that? So functions are like the most important thing in mathematics, but they're a lot more abstract than what you just learn in, I don't know, algebra or something. Because you can have anything you want in the range of the domain. In this case, again, the domain are functions, the range of vectors. We've never seen anything like that before. But here we got it. Let me go make that bold because it's important. And let me make gradient red because that's what we're defining. Any questions at all on the gradient of a function of two variables? Okay. Also, I'll say this at the end, but I don't know, I probably won't write down the formal full definition. What do you think would happen if it was an f of xyz? And you want to take the gradient?
It'd be a three-dimensional vector.
Yeah, you just go fx comma fy comma fz. Okay, the good news is you can extend this to as many variables as you want, and you just do what you would think you need to do. Okay, whatever variables you got, in order, you write that as a vector. You write the partial derivatives as a vector. So let's do an example. The examples are easy. So how about let make it a function, f of x comma y equal e to the x cosine of y minus x squared. Find the gradient. So grad of f of x comma y. And the idea is there's nothing mysterious about this. So what do you think it is? Let's see if you can do it. I know I haven't done an example yet, but I promise you there's nothing tricky. I'll start it out. So what is the gradient of f of xy? And I'll see you all jumping in the chat box or talking, but hopefully you will. Okay, so the first component. Okay, so we're gonna take the partial derivative with respect to x. Notice that we have e to the x times a constant. Derivative of e to the x times a constant is e to the x times a constant. So it's actually going to be e to the x times the cosine of y. So cosine of y is still there. It doesn't go away because we're not adding, we're multiplying. And then minus 2x. Comma. And now we need to find the derivative with respect to y. Well, e to the x is now the constant. X squared is a constant, but we're subtracting x squared, so that goes away. But the e to the x is a multiple of cosine y. The derivative of cosine y is negative the sine of y. So I get negative e to the x times the sine of y. And there's my gradient. Any questions at all on finding the gradient? I just want to let you know that if you're not good already at finding the partial derivative of a function with respect to either variable, you need to get good at it. That's all we're doing. Okay, that's what we did 2 days ago. That's what we're doing today. That's what we're going to be doing in 2 more days. And guess what? That's what we're going to be doing in, or not 2 more days. I guess that'd be 3 more days. And that's what we'll be doing a week from now. So we're going to be doing a lot of partial derivatives. Okay. Any questions at all so far? Okay. So do you need another example or do you get the idea? You all agree there's nothing too fancy? Okay. All right, so what I'm going to do is I'm going to go to directional derivatives. So this is the idea, and let me show you the map. Let's suppose we're over here by this little pond, and we want to go in that direction, and we want to say, how steep is it? Okay, it'd be nice to have a number that tells you how steep it is. Okay, and we can't just say what is f sub x or what is f sub y because that's north and east. This trail isn't a northeast trail. I mean, north only or east only trail. This trail goes moving around. That's how all trails are. So what we want to do is want to say, well, if you take one little tiny step, not north, not due north, and not due east, but due in the direction of the trail. How steep? What is the slope of the tangent line for that curve that goes along that curve, for the curve that we're looking at? Okay, so we got this curve, which is the trail. I want to say, what is the slope of the tangent line for this curve? Any questions on that? Okay, so we want to say, how steep is it? And that's our idea. And the way you find out how steep something is Again, imagine taking a step. So what you're going to do is you're going to say, okay, you're going to start out saying, all right, what is my elevation where I am right here? Then you're going to take a step to maybe right there and say, now what's my elevation? And what you're going to do is you're going to say, I'm going to take the change in elevation divided by how far I've stepped. Any questions on that? And then what you're going to do is you're going to take a limit as your length of the step goes to 0, because you want it at that spot, not just the entire trail, but where you're standing. And that's the idea of the directional derivative. So now let's define it. And it'll look somewhat similar to the way you've looked at derivatives in the past. All right, so I'm going to copy and paste, because I'm going to start out with let f of xy be a differential function. Pretty much everything we do in this class is we want a differentiable function. So let f of xy be a differential function. But now we need to say, well, what direction are we walking in? Are we walking northwest? Are we walking southeast? Right? Are we walking, I don't know, northeast? Now, how are you walking? What direction do you want to take that little step in? So if you talk about direction, then what we can do is we can say, how do you take a vector and only think of the direction? Any thoughts? So if we only want to look at the direction of a vector, what do we want to look at for that vector? How do you get rid of the magnitude? Because we don't care about the magnitude, we want the direction. Any ideas? You can do tan inverse, good. And I'm going to make it simpler than tan inverse. We're just going to look at the angle theta, okay? But now you remember that x is r cosine theta and y is r sine theta. And we're going to let r be 1, so it's a unit vector. Okay, because if you make it a unit vector, you're kind of getting rid of the magnitude. Well, if you do that, let's make this a equation. So u equal cosine of theta comma sine of theta. Be a unit vector. Because every unit vector could be written that way. Okay, and I hope you can all look at it, find the magnitude, and convince yourself that you get one. Okay, then the directional derivative of f of xy in the direction of u is defined by and now what we're going to do is we're going to think about how you take a directional derivative. How do you find a slope? It's the rise over the run. So the rise is a change in f, and the run is going to be the change, the little step change that you did. And then we're going to take a limit as that step size goes to 0. That's the idea here. So what we get, let me insert. Is going to take a limit as t approaches 0. So it kind of looks like a derivative. Don't derivatives look like that? And then there's going to be a fraction, because derivatives definitions have fractions. And you're going to have f of, and what we're going to have is x plus t cosine theta comma y plus t sine theta, and then minus f of xy all over t. Let's make that bigger because it's too hard to see as it is. Not to mention it's probably too low for you. And there is the directional derivative definition. Any questions at all on this definition? Any questions? Okay, this is it's an important definition and it comes up a lot. Again, this is just like the definition of the derivative. You take the change in the altitude, that's the f of after taking a step, minus the f of before you took a step, divided by the step size. Okay, and that's it. Okay, but I will tell you, the good news is, just like with derivatives, regular old derivatives, you don't usually have to do this, right? Right? When you take a derivative, how often do you resort to this definition? Yeah, I wouldn't say never, but rarely might be the better word. If you have data, for example, and not the equation of function, you usually have to resort to this definition. But if you have a function that's an equation, you don't have to do this. Which means, as you might guess, you have a theorem coming. And that is a theorem that tells us how to find the directional derivative. And we're going to start with this. Let f of x be f of xy be a differential function, and let u equal cosine theta sine theta be a unit vector. Okay. Okay. Oh, do you know what I didn't do? I didn't give you the notation. I probably should do that. And that is d sub u of f of xy. Is a notation for directional derivative. D for derivative, and then u because we want to go in that unit vector direction, and then f because that's our function. Okay, then, so now let's go back to the theorem. Let f of xy be a differential function. Suppose we have a unit vector u. Then d sub u of f of xy is equal to, this is one you may not have guessed, the gradient of f dotted with u. Isn't that nice?
Yeah, it's dot product instead of cross product.
Yeah, well, why would cross product be a disaster? Not just because it's harder to do, but why would it be?
Because it's not the u isn't a vector. Wait. Yeah.
U is a vector. No, u is a vector. What's the problem? This is important, by the way, to understand. Not quite about the magnitude. It's a bigger problem. It's a really bad problem. If you try crossing instead of dotting. Anyone see? Yes, two variables. Or yeah, this is an R2. You can't do a cross product in R2. You can only do a cross product in R3. So you definitely can't even talk about cross products when we're looking at this stuff. Okay, that would be a complete disaster. Hopefully you see that. It's not just hard, it's not possible. So this is definitely a dot product. Okay. So any questions on this definition? Okay, so now that, or not this definition, this theorem is what I should say. Let's boldface it so I don't lose the fact that it's a theorem. All right, well, why is this true? Okay, well, it's true for the following reason. I'm gonna actually do this. Okay, so this is kind of part of the theorem, but you don't need the equal sign to have the theorem. It's just an obvious thing. Grad f dot u is fx times t cosine theta, or times cosine theta plus fy times the sine of theta. That's just a definition of dot product. Do y'all agree? Remember, u is cosine theta sine theta. So I just took the dot product, and grad f is fx fy. Okay, what does this kind of look like? And the hint is think 2 days ago. What does this kind of look like? Something about derivatives. We have a sum of products. That's a hint. Yeah, this is a chain rule. Okay, so this is basically a chain rule. Okay, so notice this is a chain rule where we're looking at a derivative of a function times another function plus a derivative of a function times another function. Okay, any questions on that? So this is the chain rule. So this is actually the derivative of f of a function. Okay, but and I don't think I'm going to type out all the details because we only have so much time. If you look at this limit, this is also the derivative of a function of t. Do you see that? So if we think about the vector, if we think about t cosine theta, t sine theta, which is just tu, then this basically gives you the derivatives. And that's what's going on here. So I'm not going to do the full proof, but that's the idea of the proof, is that if you do a reverse chain rule of this, you end up with the derivative of f of t, and the derivative of f of t by definition is this limit. And that's the reason why this works. What I will do is I'll let you look at the textbook to go through the details of it. But I only have so much time, and I could do it, but typing it takes forever. So I'll let you look at it. Any questions on this theorem? Okay, so what the theorem tells us, the bottom line is, if you ever have a function that's written, with x's and y's, and you want to find the directional derivative, then use the theorem. We could just plot that in. You take the gradient and you dot it with your u. So let's do an example. So the example is, how about let f of xy equal, how about xy squared minus 3x plus y. And hopefully you can look at that and agree this is a differential function, by the way. Hopefully that's obvious. Okay, most things we do are differentiable. And let's suppose that u is equal to, how about the vector 1 over 2, comma, square root of 3 over 2. Okay, hopefully you're convinced that is a unit vector. Find the directional derivative of f of xy in the direction of u. Any questions on the question? Okay, well, the idea is this isn't supposed to be hard. Okay, you have two choices. You have the choice to use the definition, or you have the choice to use a theorem. What do you think is the better choice? Yeah, undeniably use a theorem. Don't even think about the definition. You could do it, it would work. Boy, it would be fun. Okay, but the theorem is pretty easy to use. So what we do is first let's find grad f. And that's not supposed to be hard. I didn't give you some evil gradient thing. So grad of f is a vector, and what vector is that? Yeah, y squared minus 3 is the I component. And the j component is going to be 2xy plus 1. Okay, so now we're ready to use a theorem that says the directional derivative in the direction of in the direction of u of f is equal to the gradient of f dotted with the vector u, which is a half, comma, root 3 over 2. And now we just do the dot product. It's no big deal. Okay, and you do the dot product, you get y squared over 2 minus 1. And then plus, we have root 3 over 2 times 2xy, which is root 3 times xy. I'll put a space there so it doesn't look like it's inside the root. Okay, and then plus root 3 over 2. Any questions at all? Any questions at all on finding the directional derivative? Okay, I don't know if I'll have to do an example of this, but if we wanted the directional derivative and we wanted to evaluate it at some value x comma y, then you just plug in x and y at the end and you get the number. Y'all see that? So if I gave you a value for x and y, you plug in. So one of the things you need to get straight, by the way, is that gradients are vectors, are directional derivatives vectors. What do you think? Yeah, directional derivatives are not vectors, they're numbers, because you took a dot product and the answer to a dot product is a number, not a vector. A couple more things I want to mention, and that is if you're given a vector that isn't a unit vector, but you still want that direction, then it's really easy. You just take the vector that you're given and divide by the magnitude and then find it. And that still works. So it doesn't have to be a unit vector to find the directional derivative in it, but you need to find the magnitude to use this theorem, this formula. Any questions on that? Okay, so there's a couple little details that might come up from time to time. And there's your directional derivative. Okay, very important, by the way. This comes up in a big way. Any questions on this? Okay, now I have a question for you. Let's suppose we have this function. We'll even do this example. Xy squared minus 3x plus y. And I don't know, how about let xy let's look at the point. How about 1, 2? And what we wanted to do, or we want to do, is we want to find out in what direction will be the steepest. So if we want to find out what direction, so what unit vector u will the directional derivative be the biggest? How do we do that? Any thoughts? Any ideas? This is actually really important. So I want to give you a chance to think about it. And if no one can think of it, I'll tell you, and we'll look at it. Okay. Maybe I'll even take a look. Got to go there. And do it with a picture. That's why I'm doing a little drawing. All right, so what we have here is we have the gradient of f dotted with u. So the gradient of f is a vector. Might look like that. We want to dot it with a unit vector and get the very largest possible answer. What direction should we go in? So if we just kind of picked a direction, this will not be the best direction, because how do you do a dot product? What's the formula for a dot product in terms of magnitude and angle? You remember? Who remembers the formula for a dot product in terms of magnitude and angle? Hoping you all jump in because you're all supposed to remember this. So V dot W is equal to
the magnitude, the components of each of them multiplied together. So like, and then no, it's the magnitude of both of them multiplied by each other, right?
There's one more piece, and the other piece is actually the most important. It's not just multiply the two magnitudes, there's another piece for the dot product. Remember? Okay, it's the magnitude of V times the magnitude of W times the angle between them. Do you remember that at all? Times, sorry, the cosine of the angle between them.
Yeah.
Okay, well, what is the magnitude of U? Yeah, this is 1. We're talking unit vectors. Okay, so the magnitude of U is meaningless because that's not going to multiply into anything, not changing anything. The magnitude of the gradient, you don't get to choose. That's the gradient. The only thing you get to choose is the angle. So now let's go back. And remember that the gradient, let's put it here in equation mode. Grad of f dotted with u is equal to the magnitude of the gradient of f is times the magnitude of u, but that's times 1, so I don't need to write it down, times the cosine of the angle between them. Okay, times the cosine of theta. Any questions on that so far? All right, so if I want this to be as big as possible, because that's what you want the steepest uphill climb you can do, what should theta be? Yeah, theta 0. Any questions on that? So what we can say is that the maximum directional derivative, let's write this down as a theorem, and that is the maximum directional derivative is in the direction of the gradient of f. And that's because if you want theta to be 0, you better be in the direction of the gradient, because that's what it means for theta to be 0. It means you're in the same direction. Okay, so that's really important. So let's go back to our beautiful contour map. What that says is that if we were looking at, a point over here, on this steep area, and you want to find out where's a rock going to fall. Okay, well, that tells you the rock is going to fall in the direction of the gradient. Any questions on that? Okay, now that we know that, how is the gradient related to the level curve in terms of directions? Any thoughts? This you might know from hiking and stuff. What direction is going to be the steepest climb, up or down, by the way? Down is negative the gradient, up is positive the gradient. And how does that relate to the level curve? Any ideas? Level curve. Okay, first thing, the gradient is a vector, right? Level curve's a curve. Any ideas? Okay, so again, if the rock is going to fall, and it's right here where my point is, where's it going to go? And it's going to go perpendicular to the level curve because the level curve is level. Does that make sense? So it'll always go perpendicular to the level curve. Any questions on that? Write down another theorem. These are all properties, but these are just individual theorems for properties. The gradient of a function is perpendicular. And let me write down another word for that, orthogonal. Means the same thing, to the level curve at that point. Any questions on that? Okay. Any questions? Okay, and one way of seeing that is we know that if you look at a level curve, the direction of the level curve, let's go over here. Let's go back to the definition. So if you're on a level curve and you move a little bit along that level curve, you haven't moved. You all agree? So that means the directional derivative is 0 along the level curve, right? There's 0 steepness. Any questions on that? So there's 0 steepness. Well, if you want 0 steepness, let me go back to this little definition here. What will theta be if you want 0? Pi over 2. And that's the definition of perpendicular. Means you're at a pi over 2 angle from the gradient. Okay, so that's the proof right there. Is it comes from grad f dot u. If you want it to be 0, then theta better be pi over 2. Okay, negative pi over 2, but that's the same thing. Still perpendicular. Any questions on that? Okay, theorem. This is a very important theorem too. These are all really important, by the way. Okay, if the gradient of f of x comma y, let's call it x, let's call it AB. So I'm plugging in a point, is equal to 0. What does that tell you? What does that tell you about the directional derivatives? If the very biggest you could be is 0, what do you know about what you are in any direction? Any thoughts? Okay, if the highest you could be is 0, and by the way, negative the gradient will be the minimum. That means the lowest you could be is 0. How high are you? This isn't supposed to be hard. If the highest you could be is 0 and the lowest you could be is 0, how high are you? Anywhere. 0. Exactly. So the directional derivative is 0 for every direction. Any questions on that? Okay, now we're going to spend some time on this in 2 days. What do you think it looks like if du of is always 0 in every direction? Let's say you're hiking. Where are you? Or where might you be? Any thoughts? Yeah, you could be at the bottom of the valley. Or where else could you be? Bottom of the valley or the... Yeah, the peak. Okay, the top of the mountain, the bottom of the valley. You could also be on the saddle, if it happens to be a saddle point. So there's different places you can be, but it turns out it's really important. So if the directional derivative is always 0, that's a really important point. And we're gonna spend the entire time next time talking about that. Any questions on these theorems? Okay, let me do this theorem. I'm just going to copy and paste it because there's not much to say. And that is the minimum directional derivative is in the direction of negative the gradient. In other words, if going forward is the very steepest you can go, turn around, and then you'll be going steepest downwards. Does that make sense? That's all that says. Okay, it's kind of obvious. There's not much to say. Any questions at all on any of this? Okay. I want to mention this works for 3 dimensions. As I said, I'm not going to write it all out, but everything I said works in X, Y, Z. It works in 10 dimensions. It works in every dimension. Okay. Besides hiking, I like hiking, but you don't make a whole lot of money hiking, by the way. Where do you think this is really important? And the hint is, if you can do this very well, and someone offers you a job for $95,000 a year, laugh at them because they're not paying you enough. Okay, if you're doing this particular job. Any guess? Yeah, AI. Okay, the way AI works is the computer has to learn which is the most efficient way of getting somewhere. Does that make sense? So the computer is going to start with a guess and try to get to the very best answer. And that's kind of what AI is all about. And it's going to learn what the best answer is from a bunch of data. And then it's going to do the best answer, and that's how it's going to react. And the method that AI programmers use, it's probably the most common method. It's called gradient ascent. Sometimes gradient descent, whether you want to get high or low. And what that means, let me just show you on a map, but again, in AI, there's no not really elevation. It's ideas. It means if you're starting at a point and you want to go from here to over here, then what you're going to do is you're going to go in the direction of the gradient, and that'll get you down as fast as possible down that mountain. Do you see that? So if you want to get down that mountain as fast as possible, you go in, you take a step in the direction of the gradient, you recompute the gradient, you take another step, and you keep going. Okay? And actually, that would be going up the mountain. Down the mountain would be negative the gradient. And that's how AI works. I can't get into the details of it because it's pretty complex. There's a reason why you get paid that kind of money, not just because you know how to take a partial derivative, but you know how to use the gradient in creative ways. And if you can do that, you can make big money right now. It's one of the major places where employers are looking for to be able to be more efficient, because a gradient will do a maximal efficiency. So that's just a note. Again, I can't show you the details because it's too hard, but I can tell you this is the way it is. And I've talked to AI programmers. That's what they do for a living, and I've done a little myself. That's how you do it. Okay, any questions? Okay, we've pretty much done everything. Again, 3 dimensions, I'm just saying it's the same. You do exactly the same thing. And that's it. The only thing is, you're not really going to have a cosine theta, sine theta for x and y. You're going to have just a unit vector. But you do the same thing. You take a vector, divide by magnitude, and then everything else still works. Okay, well, we're just about out of time. So I'm going to stop my share. And I'm going to stop the recording.